Now let's look at the analysis of the marching cube algorithm. So the running time of the marching cube algorithm is actually dependent on the number of grid cells. So we are actually running the algorithm through every grid and finding the corresponding isosurfaces for that particular grid. And so it's linear in the number of grid cells. But we've already seen that every grid cell may not contain an isosurface. So that is actually wastage, because you don't necessarily have to run through the uh, entire set of grids. So we only have to maybe run through the grids where we have isosurfaces. So, but this is amenable to parallelization. So each cell can be processed parallelly. So this is uh, decent. We can do parallelization on this, and we can get GPU implementations of this. Okay, that is regarding the running time of the marching cubes or marching squares algorithm. And regarding the output size, outputs are actually triangles in this case. Depends on the number of cells containing the isosurface. As if you have more cells with isosurface, then you have more triangles. So can it be reduced is one question. It can be reduced by increasing the number of size of the cell, or by adjusting the resolution of the grid. That is one way to do it. But then you get a lesser isosurface with lesser resolution or lesser detail. Fine. Also, there is a variant called as marching tetrahedra. So in marching tetrahedra, rather than marching as grids, you march in the form of tetrahedra, which by splitting a grid into four tetrahedra, I suppose. Okay, we'll look at it later. So then the number of isosceles triangles are actually more. The ambiguity is less, and the running time is also more. We'll look at these cases, marching tetrahedra later in this lecture. So we looked at marching cubes ambiguity. For marching cubes, or even the 2D version of it known as marching squares, there is one ambiguous case. It arises because of the confusion which we have on how to connect the ISO points. We only have 4 ISO points. How do we connect between them? So in marching cubes, we have several cases of them. And how do we solve this? We solve this using the asymptotic decider. And most of the cases are, for the marching squares, asymptotic decider actually settles the issue. For marching cubes, still there could be some cases which are not resolved by the asymptotic decider. So we have techniques which are actually based on trilinear interpolation and understanding the voxel connectivity uh, between the isopoints which are lying in the interior or exterior of the isosurface. So there are multiple ways of doing this. Now let's look at the marching tetrahedra setting. So in the 2D case, we have actually, sorry, it's not 2D case. Yeah, it has only actually have two cases where, so in tetrahedra, we only have 4 edges for this 3D shape. And there are only 2 cases where you have a positive and 3 negatives, or three positive and negative is actually a similar case, symmetric case to that. And the other cases where you have 2 positives and 2 negatives. Okay, those are the 2 cases. In the case where you have a single positive and 3 negatives, or the other single negative and 3 positives, you get a triangle as the isosurface. And in 2 positive and 2 negative case, you basically get a quad which can be separated into two triangles. So here, all these interpolations are piecewise interpolations. And also there is no ambiguity. But the issue is we have a smaller marching size. Each grid can be divided into 6 tetrahedra. So marching is input size is much more larger, and also since the input size is larger, you have more number of isosurface triangles. So that is one drawback of using marching tetrahedra, but we can do it with all the ambiguities. in this margin tutorial algorithm. Also, we have multi-resolution isosurfaces, which I've discussed earlier, where we can reduce the number of triangles by changing the resolution of the grid, which we're using to march through. Also, if you have to obtain multiple isosurface from the same data, then we have to use some kind of shaded isosurface, where we have to use some kind of lighting and all those things, and transparency to obtain multiple isosurfaces in the same image. So this concludes the discussion on isosurface extraction and marching cubes.